Hey guys, this is going to be a relatively long one. I'm going to give you the heads up today, so I'm going to kind of keep it light on the work side for today. But I'm just going to try to get through the volcano chapter and really highlight the information that is most important because we need, now that it's quarter four, we need to move on to the space stuff. So we're going to talk about volcanoes and some igneous activity. This will be on here. The PowerPoint's on there. So take notes, on stuff that's kind of important. So with volcanic eruptions, there are a few different parts of it that decide whether you have a violent eruption or a quiet eruption. And basically the three are the composition of the magma, so what it's made of, the temperature of the magma, so how hot it is, and how many dissolved gases are in the magma. This all factors into the viscosity of the magma. And viscosity in general is just a material's resistance to flow. So different factors affecting the viscosity are same things here. So temperature. So hotter magmas are less viscous, so they are runnier. So the hotter a magma gets, the runnier it gets. Composition. High silica equals high viscosity, and that's things like rhyolite. Rhyolite was the pink rock that we looked at that was during the Rock ID lab, and that's what's under Yellowstone. It's very highly viscous. It does not run very well at all. Then you have a low silica magma. These are things like basalt, so basaltic magma. This is what comes out of Kilauea in Hawaii. These are much more fluid, and this is the reason why Kilauea, for the most part, just kind of keeps bubbling out. And then finally, the dissolved gases. Most of the dissolved gases that we are talking about here are water vapor and carbon dioxide. And the problem that you get is that as the gases get up near the surface, the pressure on them is much less. So what happens is that with decreasing pressure comes increasing volume. So they expand a lot when they get up near the surface, and that expansion produces a bunch of pressure. And that pressure is going to be what makes it so that it wants to come out. So they provide the force to extrude the lava. That just basically means to force it out of the volcano. The violence of an eruption is related to how easily the gases escape from the magma. So if they escape easily, then you have a more fluid magma. If it's not, then you have a little bit chunkier magma. So viscous magma produces a more violent eruption. So there are two basic types of lava flows. One is called Pawewe. That resembles braids and ropes. I'm going to show you a picture. It actually just looks like a pile of ropes. And then we have one that's called A'a, which is not as smooth and it has more jagged and rough blocks. Gases overall make up 1 to 5% of the magma by weight. That doesn't sound like much, but if you think about how much gas weighs and the density of gas versus the density of rock, you start to understand that there's actually a lot of gas in there. And those gases are mostly carbon dioxide and water vapor. So here's Pawewe. Like I said, it ends up looking kind of like a pile of ropes. So that's what Pawewe looks like. This is A'a. So much chunkier, more jagged. This is old Pawewe flow that's been weathered, which has made it even more smooth than it was before. Next, we're going to talk about the parts of a volcano. Make sure you know the diagram that's going to be on one of the upcoming slides. If we do have class again this year and all that, and we have a final, that anatomy of a volcano slide will definitely be on there. So we have the conduit or pipe, which carries the gas-rich magma to the surface. So that goes right up the middle. The vent is right where that pipe meets the crater at the top. So that's the surface opening. The crater is the steep-walled depression at the summit. And then the caldera is a depression that's even bigger. So imagine if the crater at the top of the volcano was bigger than a kilometer. They're made slightly different, so I'll show you kind of how that happens. And then you have some other things called parasitic cones and fumaroles, and these are basically ways to kind of get some of the pressure to release in other ways. So I'll show you what those look like. So here is the picture. So as you can see, here's the conduit. The conduit leads from the magma chamber up to the top. This is the vent is right up top here, and the crater is the very top where it's coming out. So this is a composite cone volcano. Composite generally means made of different stuff. So here you can see different layers of this darker stuff and the lighter stuff layered and layered over time. So that's why this is called a composite. You can see the parasitic cone coming out to the side over here. And so when I think parasite, I think it's something that kind of sucks the blood or energy out of something. So this is actually taking some of the magma and kind of sapping some of the energy so it comes out the side rather than everything coming up the top. Then you have some lava. Here it's showing lava coming down the side. And hardened lava makes up part of the layers of the volcano. And then the pyroclastic material that comes out the top also makes up some of these other layers down here. So that's why it's pointing both at the layers down of the volcano and the stuff that's up in the air. So different types of volcanoes. We have shield volcanoes, which are very, very large. These are the biggest, but they're more slightly domed and very broad, mostly made of basaltic lava, generally large in size, and Mauna Loa in Hawaii, which is basically on the same island that Kilauea is on, is an example of this. And Mauna Loa is actually the largest mountain in the world if you start from the base all the way up to the top, because it starts at the bottom of the ocean. Then you have cinder cones. These are built from ejected lava fragments. Very steep slope angle, small in size, and a lot of times they happen in groups. These things are made over periods of weeks to months, not thousands of years or tens of thousands of years or anything like that. These happen very, very quickly. There are a bunch of them down in Mexico right now. They kind of look like anthills. And then composite cones. These are the classic volcanoes that probably most of us think of when we think of what a volcano looks like. So the other name for that is a stratovolcano. Most are adjacent to the Pacific Ocean, so think Ring of Fire. So these are a lot of your Ring of Fire volcanoes. Large size, interbedded lavas and pyroclastics. Like I said, composite means layers of different things, and these tend to have the most violent type of activity, so explosive eruptions. As far as different volcanic hazards, I'm not going to spend tons of time going through this. Don't worry about taking notes. Here it shows volcanic ash can cause damage to plant life, can cause damage to animals. If you're ever in an area where there's a volcanic eruption, understand that volcanic ash is actually really bad to breathe in, so you need to wear a mask. Obviously, there's lava and pyroclastic materials and stuff like that. So these are all different volcanic hazards. Pyroclastic flow is one of the most magnificent things. Comes down, it looks kind of just like a cloud, but as it showing, it can be 400 degrees Celsius. And basically all the stuff inside here is on fire. If you watch a video of pyroclastic flow at night, it looks totally different than what it does during the day. Other volcanic landforms. So we talked about calderas a little bit, and this is going to show you basically how that works. There's steep walled depressions up at the summit, and these are formed when the volcanoes collapse. They're usually nearly circular, and their size exceeds 1 kilometer in diameter. So this is basically what happens. You have all this pressure that builds up from down below, and pushes up, and eventually the volcano collapses back down into the magma chamber a little bit, and that's what's going to eventually lead to the caldera forming here, and a lot of them will actually end up filling in with water. So this is Crater Lake. I think this is in Mount Hood in Oregon, and so this is, down below here, you have a very large volcano. This is showing Yellowstone. Yellowstone is what we call a supervolcano. Um, Probably more destructive potential than anything else that we know about. If you look at where the ash falls from the last few eruptions happen, you can kind of see how big it is. One of the things, if you just take a look at the timeline here, so this is the ash fall from 2.1 million years ago, then 1.3 million years ago, then 0.64. That puts us somewhere about about the time when this thing should be blowing up any time now, and if it does, that's going to cause much grief, um, because as you can see from this ash fall, this is absolutely huge. It will cause a lot of damage and disruption. So these are some landforms, especially if you go out west, you'll tend to see a lot of these. So think of these as being the things that are left behind after volcanoes. So what happens after that magma hardens? What kind of landforms do you get? So this is, and you don't need to take notes on this, but this is what's called a volcanic neck. So this is when the conduit or pipe and the magma in there hardens, you end up getting this like vertical looking formation that happens like this. Gets weathered down over time, so this used to be a lot higher. But as you can see, this is 1,700 feet uh, as it is now. So it used to be much bigger. Then these are different types of things that can happen when the magma chamber hardens up. You can get things like batholiths, where this structure over here, each one of these things that looks like a mountain, that was a magma chamber at one point, and weathering and erosion has just eroded all the stuff around it. Then you can get sills and dikes and things like that. I'll show you some pictures of those. So here is a sill. When I think of sills, I think window sills. They're flat. So you can see that this is an igneous, the very top of the sill is an igneous layer that's horizontal. And then you have some sedimentary layers underneath it. But the igneous layer is stopping the weathering and erosion. So that's why you end up with these mesas. This is a dike. This is basically when you have like a fissure eruption. So you have a crack and the magma comes up and fills in the crack, and then everything around it weathers and erodes. So you end up with what looks like a spine. Like I said a couple minutes ago, laccoliths and batholiths are they're either parts or full magma chambers that get exposed over time. And this is just showing what a laccolith looks like. As far as where we see igneous, most volcanoes, I should say igneous activity, most volcanoes are located on the margins of the ocean basins. So think, once again, ring of fire, because you have the whole Pacific plate. And then you get second group is confined to the deep ocean basins, and that's where we get basaltic lavas. And then you get the third group includes those found in the interiors of continents. So what are we talking about here? So here are the ones that are in the middle of ocean plates. So that's where you get the basaltic lavas. This is a hot spot. Here's around the edge. So this is the first example. And then the third are inside the continental margins over here. So those are your three types of examples. So obviously plate motion provides the mechanism by which all this is formed. So you get the descending plate that partially melts. Then as it melts, it gives it upward force because it becomes less dense. Rising magma can form volcanic island arcs and continental volcanic arcs, which we've already kind of talked about a little bit. But this shows you kind of how that happens. Here's the subducting ocean plate that goes down. And it gets partially melted down here. And that melting stuff creates the upward pressure to form this volcanic island arc over here. We also get a bunch of volcanism at divergent plate boundaries. As the lithospheric plates pull apart, there's less pressure on the underlying rock, so partial melting here occurs, and then the magma comes up to fill in the gaps. This is what we see in areas where there's seafloor spreading. So here's our example. So the two lithospheric plates pulling apart, and then the magma chamber will start to form below it. And so you start to make things like the mid-oceanic ridge form there.